All right. Oh, and also Taha, for your information, I think you probably have noticed, but in case you haven't, also shared with you is this document called Links to the Recordings. So here we have all the links to the recordings of all the lessons that we do one by one. And so lessons 1, 2, 3, and 4 have all been recorded. You can go back and listen to the material that we talked about as well. Last lesson, lesson number 4, there was a few YouTube videos that I showed in class just to have a better feel for proteins and enzymes and how they work. You can watch those as well. And then after today's lesson, I'm going to go ahead and also put on the link for the recording from this lesson and every lesson from here on. Okay, so those resources are all also available to all the students. All right, so Unit 2 is about processes. Oh, and now we have another new student joining in. Hello, Nagar. Hi, Nagar. Welcome to our grade 12 biology class. I just went through sharing some new information with another student, and if you like, after class, if you could stay for a few minutes and I will bring you up to speed on everything as well. But I was just actually about to start our lesson. So we're starting Unit 2, and Unit 2 is about metabolic processes and how they relate to the way that plants and animal cells produce energy and the processes that are related to energy production and energy consumption and how those processes are interrelated. And we're going to be examining a lot of these ideas that you were probably introduced to in your previous biology course, in your grade 11 biology course. But here we're going to talk about them in a lot more detail. And here are some expectations of after you've gone through this unit. These are the things you're going to be talking about, but especially our first lesson of the unit, we're going to be discussing some thermodynamics. And thermodynamics is something that you should be very familiar with if you've taken a chemistry course. And obviously, there's a lot of overlap between biology and chemistry. So one of the important characteristics that differentiates living matter from non-living matter is their ability to be able to manipulate their external environment, their habitat. And the most important of these manipulations is the manipulation of energy, to be able to put energy into different forms. For us humans, this might be as basic as when in ancient times, early man was learning how to control fire and create heat and light, or it could be as complicated as today, how we use nuclear or hydroelectric power to provide electricity for our homes and our cities. But whether or not this is a very simple manipulation or a very complicated one, it basically has got one factor, and that is that the converting of a less useful form of energy to something that is more usable for us. Now, these energy conversions typically make our lives easier. They allow us to convert electricity into maybe energy of motion, which is kinetic energy, perhaps to power various equipment and various processes, or our electric cars. Or it might be to create heat to toast our bread in the morning for breakfast. But if you look at it even on a cellular level, for all living things, there is a constant infusion and input of energy that is required for the development and the maintenance of the cell's processes. And the source of this energy ultimately, and actually the source of all energy ultimately on our Earth, is the sun. And solar energy can't be used by living things such as us directly, but instead it has to be converted into a form that can be more usable. So plants initially do this for us. They trap the sun's energy and convert it into a chemical energy, which then they store it in the form of an organic molecule such as glucose. And that energy that was taken up, that radiant energy that was absorbed from the sun that got converted into a chemical energy, is actually stored in the bonds of those organic molecules. So the bonds of a sugar molecule, for example, that the plant produces by absorbing sunlight, that energy from the sun is actually present within the bonds of that molecule of glucose. So then when you have herbivores or other animals that might then consume these plants, they eat them and they break down those organic molecules, therefore releasing the energy that was stored in the bonds of those organic molecules to be able to power their cells and themselves. And then carnivorous animals then that don't eat the plants eat these herbivores, for example, and capture the energy from eating the herbivores, which consumed the plants, which took radiant energy from the sun. And so this cycle of energy capture, release, and transformation is a cycle that just continues. At the cellular level, these processes that take place are responsible for being able to extract the energy from the chemical bonds of food, of molecules such as glucose. And in all of these cases, that energy conversion that takes place is subject to the laws of thermodynamics. And when we talk about thermodynamics, what we are talking about is thermo, meaning heat, and dynamics. And something that is dynamic is changing. So the changing of heat. And as such, these metabolic processes, these cellular metabolic processes, are made more difficult by having to balance the release of energy with the resulting release of heat, which, if it's done in an uncontrolled way, if a whole lot of heat energy is suddenly released, it can actually cause damage to the cellular structure. So how is it that then we are able to consume sugar and basically break down the sugar in a reaction that is very much similar to combustion of sugar, so burning of sugar? How is it that we can use this energy without ourselves being burst into flames? Well, us and other organisms have developed a very complex set of metabolic pathways that allow for the slow and controlled release of energy so that it's not all released in one shot. So in today's lesson, then we are going to cover those laws of thermodynamics and use them to explain energy transfer in the cell during the processes of photosynthesis and cellular respiration. We are going to use the appropriate terminology that is related to these laws of thermodynamics, and the appropriate terminology is words such as metabolism, entropy and enthalpy, endergonic versus exergonic, endothermic versus exothermic, and what is free bond energy and free energy. So here's just something for us to think about as we are going through our lesson today. And that is, if you were to take a deck of ordinary playing cards, hold them in our hand and flex them until they kind of fly out of our hands and spring free, and then go all over the place. Obviously, that's typically what happens when you bend and let a deck of cards spring free and go all over the place. Then what happens? Then you have to clean it up. So if you were to actually time how long it's going to take us to pick up every single one of these decks and put them, every single one of these cards and put it together in a nice tidy stack back into our hands, we can get an understanding of it certainly takes a lot longer and more energy needs to be put into putting things back in order than it did for us to create that random, messy chaos to begin with. So things that you can think about as it applies to the idea of thermodynamics is what type of energy do you think the cards use when they are flying out of our hands? Think about that. And did it require more energy to put the cards in order back into a stack, or to make the disorder and let them fly free all over the place? And finally, how do you think order and disorder are related to energy within the cell? So these are things you can keep in mind as we are going through our lessons. Does anybody have any questions so far? All right, so again, thermodynamics is the science that deals with the transformation of energy in all of its forms. And as though we talk about, when we break down the word thermodynamics, it literally means change of heat. The thermo part means heat, dynamics means change. So literally, if you take it apart, what you're really talking about is change of heat. But all forms of energy, if you think about it, are eventually degraded down to heat. So in a way, the rules that apply to this change of heat and heat transformation also apply to energy changes, all kinds of energy changes in general. Now, energy is the ability to do work, and work is defined as the force that is applied and operating through a distance. Now, biologically speaking, energy is used to counteract, to offset that natural physical tendency, such as, for example, the diffusion of molecule down a concentration of gradient. So the diffusion of molecule down a concentration gradient doesn't require any energy, but try to counteract that. Try to get that molecule now to diffuse in the opposite direction against the concentration gradient. And we talked about this idea a little bit last class. That is a process that takes energy. It requires an input of energy. So energy can exist in many, many forms. And as we talked about earlier, some of these forms are more useful, some of them are less useful, and as they apply to how we want to use them, how living things might want to use them. And so let's talk about some of these forms of energy. They can be in the form of heat, they can be in the form of mechanical energy, chemical energy, radiant energy. So heat energy is that energy that's associated when you have the rapid movement of molecules in matter. So that movement of molecules produces heat. Mechanical energy is that energy associated with the motion of objects, with the motion of molecules. There's mechanical energy in that, which eventually will produce heat. There's also chemical energy. Chemical energy is, as we talked about, that energy that is contained within the bonds that hold atoms together within a molecule. So if you have a molecule made up of all of these atoms that are bound together, that chemical energy is stored within those bonds holding those atoms together. Then there's radiant energy. We talked about radiant energy is that source of energy for all living things here on Earth, and it's derived from the sun. Ultimately, all of these types of energy can be found in a form such as kinetic energy, for example, in a falling stone, or in the form of a potential form of energy. So if you have a stone, for example, or a ball that might be falling from a height, as it's falling, it has kinetic energy. Or if it's positioned on top of a hill, or if it's positioned on top of a table, for example, at that point, what it has is a potential form of energy, potential energy. And that refers to stored energy. So if we look at this diagram, for example, of this diver diving off of the platform, as it's up here standing, it has potential energy. All of its energy is in the form of potential energy. And since it's not moving yet, it hasn't dove off the diving board yet, it doesn't have any kinetic energy. All of the energy is in the form of a potential energy stored right up here, waiting for this diver to leap off and go down towards the swimming pool. Now, as the diver dives off, a certain amount of that potential energy is now converted to kinetic energy. But depending on how high it still is before it finally reaches its final surface of the water here, it still has a certain amount of potential energy. And if we compare to this position here where the diver is lower down, at this position, it has less kinetic energy and more potential energy. Whereas down here, it has higher kinetic energy and lower potential energy. And this is a typo here. Kinetic energy is with a Ki. This diagram has got a spelling mistake. So when we talk about that, it's kinetic energy with a Ki, kinetic. So these laws of thermodynamics really govern all the transformation of energy that take place in our natural world. The first law of thermodynamics, which I'm sure probably all of you are familiar with, is also known as the law of conservation of energy. And it states that the total energy in the universe is constant. It's absolutely constant. And that energy can't be created, it can't be destroyed, it can merely be transferred or transformed from one form to another. And what this really means, if we think about it in layman's terms, it means that when an object gains energy, there must be a loss of energy somewhere else in the universe. That's basically what it comes down to, put into very plain, simple language. Now, in the biotic or living environment, the radiant energy that is from the sun gets transformed into chemical energy for storage within an organism. For example, this flower, this plant, absorbs radiant energy, and under the process of photosynthesis, transforms that radiant energy and stores it in the form of glucose. The energy from the sun then gets stored in the bonds of the atoms in a molecule of glucose. And now this plant that has got this chemical energy that is stored up, when this energy is then required to power various cellular functions and the growth of this plant, for example, that stored chemical energy, again, is transformed to a form that the cell can use. And this usable form of energy for cells is a molecule called ATP, adenosine triphosphate. And this ATP molecule is the primary energy transferring compound. A lot of people refer to, in science, we can refer to this molecule of ATP as the energy currency of the cell. So, and that's how energy gets transferred through this molecule of ATP. And how does this transformation occur? The transformation of transforming radiant energy to chemical energy takes place through a process of photosynthesis, but the transformation to transform this chemical energy into that other usable energy currency takes place through the process of cellular respiration. And I'm sure a lot of you are familiar with photosynthesis and cellular respiration. And in cellular respiration, this is the process by which a molecule of glucose gets broken down and releasing not only the byproducts of, when glucose gets broken down, the byproducts are carbon dioxide and water, but it releases energy through the whole action of the bonds being broken down. And here is a basic reaction of photosynthesis, where you have carbon dioxide and water plus energy, and this is sunlight, radiant energy, producing glucose and oxygen. And this, the bonds within this glucose molecule is where all of this energy has now been stored, and also within the bonds of the oxygen, of course. And in these scenarios, energy is being really transferred and transformed from one type into another. Remember, it is not being made, it's not being destroyed, it's just being transformed from radiant energy to chemical energy. But keep in mind that never do we have 100% efficiency in any of these energy transformations. Regardless of what type of transformation we're taking place, some of that available energy is transformed into heat. And so in a way, some of that useful energy will be lost in the form of heat. And in living systems, that primary potential energy source is chemical energy. And these organic molecules, such as glucose, have a certain amount of stability because of the bonds that's holding their atoms together in a particular arrangement. And as we talked about in our last unit, whenever you have these covalent bonds that are quite stable because they have their full outer valence shell, therefore they are very, very stable. But sometimes you have some bond arrangements that may not be as stable as other ones which are more stable. So it all depends on how these bond arrangements are and how stable or labile they are. So here we've been talking a little bit about the storage of energy in the form of the bonds that are holding the atoms of these molecules together. We've been talking about bond energy. So bond energy then is really an indication, it's a measure of the stability of the covalent bonds that are holding the atoms together. And the unit that we measure it by is kilojoules. And it can be quantified. You can actually put a quantity, a number to it. And it can be quantified as the amount of energy that is required to break 1 mole of the bonds between 2 atoms. And it is also equal to the amount of energy that is released when that bond gets formed. For example, if we look at a carbon-carbon bond, as we may have in a molecule such as glucose, the carbon-carbon bond requires 346 kilojoules per mole to break it apart. If you compare that to a carbon-oxygen double bond, that requires 799 kilojoules per mole. almost twice as much. So really, the type of bond between different atoms has got a lot to do with how much energy it takes to break it apart, or how much energy is released when the bond is formed. So when you have a chemical reaction of reactants going to form certain products, the reactants, or in other words, your molecules that you're starting out with, those, in order to become the products, first have to be broken apart, and then the product molecules need to be formed. So you have to break them apart and then put them back together in a different arrangement, a different combination to give the products. When you have energy or heat applied to the reactant molecules, the bonds will absorb the energy until they get to the point of breaking apart. If you have a chemical reaction that releases more energy than it uses up, that type of chemical reaction is an exothermic reaction. And the exo part means out, and thermic means heat. Exothermic, so putting heat out. It releases heat, it releases energy, so it's exothermic, it's putting it out. And if you have a type of reaction where you require more heat to be input into the system than is released at the end of the reaction, in that case, you have an endothermic reaction. And in this case, endo means in, and thermic means heat. It means this energy, this reaction is absorbing heat energy. It's endothermic. And one of the very most common and useful exothermic reactions taking place in living organisms that we have already touched on a number of times, and I hope you guys will remember that this reaction is very important and make sure you understand it well, you know it well, is combustion. And in this case, it's the combustion of glucose. So this is a molecule of glucose. And whenever you have a combustion reaction, a combustion of anything, in this case, it's glucose, but this could be anything. It could be a form of alcohol, it could be methane, it could be whatever. Whenever you have a combustion reaction, the reaction is taking place with whatever molecule you're combusting, and it is reacting with some oxygen, and it is producing nothing but carbon dioxide and water. And that defines a complete combustion reaction, where you are burning whatever substance it is with oxygen, and the end result is nothing but carbon dioxide and water. Now, the energy change that is associated with this combustion reaction is called the heat of combustion. And we give that a symbol of delta H, and we give it a subscript of combustion to indicate that this delta H, this heat that we're talking about, has got to do with combustion. So during this process, we have glucose combining with oxygen and releasing carbon dioxide and water vapor. And the overall reaction for glucose is written like this. And the delta H of combustion is 2,870 kilojoules per mole of glucose. So that's how much energy is produced when 1 mole of glucose goes through a combustion reaction. So here, remember, we talked a little bit about the endothermic and the exothermic reactions, where in the exothermic reaction, there's more heat released than is used. In endothermic reaction, more heat enters the system than is released. So if we look at that, the endothermic and the exothermic reaction in this type of diagram, and these are called energy diagrams, where on the vertical axis, we have the chemical potential energy displayed, and on the horizontal axis, we have the reaction progress. So from the start to the finish, or in other words, from reactants who undergo some sort of a transition state and then finish off at the products. Again, on this panel, to reactants towards products. So here in this case, where we start off with reactants that start off with a higher chemical potential energy, and once the reaction is finished, the products are at a lower chemical potential energy compared to the reactants. So overall, you can see that there is a net amount of energy that was released. The products have lower chemical potential energy. So some energy must have been released. So this indicates, whenever you have this sort of energy plot, this is indicative of, I hope you can all agree that this is indicative of an exothermic reaction where energy is released. The products have less energy, so energy has been released. Now on this panel, you have the other type of reaction, the endothermic reaction, where the reactants start off at a lower chemical potential energy. And then by the time you have your products, the products are at a higher potential energy. They have gained a certain amount of potential energy to go from this position to this position in chemical potential energy. So this represents an endothermic reaction where the system has absorbed heat, there's been an input of heat entering the system. And as always, there's always homework questions to make sure you guys try it. I don't grade homework questions. There's no grade associated with them, but I think it's very important for you guys to go ahead and try to answer some of these types of questions. And if you have any questions, if you want, we can go over them. You are certainly free to ask me if you have trouble answering them. But doing these questions is excellent preparation and for any midterm or exam, and it also really helps with your understanding of the material for this course. So there we talked about the first law of thermodynamics, the law of conservation of energy. Total amount of energy in the universe is constant. Energy can't be created or destroyed. It can merely be transformed or transferred. The second law of thermodynamics, this law focuses on the consequences of those energy transformations that the first law talks about. So what are the consequences of these energy transformations? In any transformation, energy tends to become increasingly unavailable in the form of useful energy that can be actually used to produce work. And since useful work is associated with producing things that are in order in the universe, this law can really be expressed as a measure of a tendency for a system to go towards an increasingly chaotic, disordered, and random state. The term we give to this disorder in terms of energy is the term entropy. And so the second law of thermodynamics says that the entropy of the universe increases with any change that occurs. So anytime you have these energy transformations or energy transfers, ultimately some of that useful energy gets lost, and usually lost to the form of heat, not very useful work. And so what that results in, it results in an increase in the entropy of the universe, an increase in the disorder, increase in the randomness and chaos of the universe as a whole. So there is this unstoppable tendency towards randomness. And if you think about it, that kind of applies to our everyday life, everyday situations as well. If you think about it, if you stop cleaning your house, what happens? It certainly happens at my house quite easily, quite unstoppably. If we start cleaning, if we stop tidying, if we don't do any of those activities, it very quickly becomes disorganized and chaotic. So much of that increasing entropy in the universe is not as noticeable because it takes the form of an increasing amount of heat, which is in the form of increasing molecular motion, that random molecular motion. So for us, it's not necessarily so observable in that sense, but we can certainly relate to how every transformation and how every transfer of energy increases the randomness overall in the universe. So overall, when we are combining these two laws of thermodynamics, the first and the second law, we can conclude that the amount of energy in the universe does stay constant, but its quality changes. The quality doesn't remain constant. So organisms use energy as a way of decreasing their own entropy for putting things in order within their cells and putting it into chemical energy and storage molecules and creating ordered structures. But this takes place at the expense of creating an increasingly chaotic and random universe by increasing entropy in the universe elsewhere. Anybody have any questions? Okay, so now we've talked about the energy that organisms use to power their cells. And in terms of thermodynamics, this energy is referred to as free energy. This is that portion of the system's energy that can be used to perform work. At any time there is, for example, uniform temperature throughout the system, as is in living cells, then the quantity, the amount of free energy that is available in the system, which we can call, give the symbol letter G, can be represented by this equation. And there are two components to G, to free energy. This G represents free energy. There's two components to G, and you can see it in the equation. The delta H and its entropy, which is represented by S, and the temperature, which is typically constant when you have a living organism. So this equation here represents the free energy in a system, in an organism. And T is typically written, the units for measuring T, temperature, in this equation is in the form of Kelvin, and Kelvin is equal to whatever degrees Celsius you have plus 273. And I'm sure most of you probably know that. But here, notice that temperature tends to amplify the effects of entropy, this entropy temperature term of the equation. So with increasing temperature, you will get increasing entropy. And this seems to be pretty reasonable, since temperature is a measure of the intensity of random type of molecular motion. And molecular motion produces heat, which tends to be a disruption to order. It disorders things. So overall, this equation shows that not all of the energy of the cell is stored in the form of available work, since some of that energy will be lost to more disorder. The factor S is for disorder or entropy. Like these. And unusable form, which is heat. So this TS factor is always taking away from our free energy. It's delta H, and a certain amount of it is lost to heat and entropy. And he represents absolute temperature in Kelvin. Free energy, just say that is G. So we can use this equation for free energy, Gibbs free energy, to help us predict what can and cannot occur in nature, or more specifically in chemical reactions that are taking place in nature in biological systems, as related to our course. And some of these types of reactions, some of these events occur quite spontaneously without outside help, while other ones will not. They will not require, they will require some input of energy, will not take place spontaneously. A good example is, you know, that if you have water, water tends to flow quite easily downhill. There's no energy required to force water to flow downhill. And you can use that flowing downhill water, you can use that to then turn, for example, a turbine in a power plant, and to be able to spontaneously take that energy and harness it to perform work, to turn the turbine and to create, to maybe change it to another form of energy, such as electricity. But suppose then you wanted to move water back uphill. To move water uphill, that is not something that takes place spontaneously. You need an external source of energy. You need to put in some form of energy, maybe pump it, maybe put it in a bucket and carry it with your own energy, with your own mechanical energy, to move water uphill against the gravity. And that is not a spontaneous process, and that is a process that requires an input of energy. In living systems, the stability of a system will increase when you have a spontaneous process happening. Something that happens very spontaneously tends to lead to more stability. And when you have unstable systems, they typically want to become more stable and will change in a way, will tend to go through some sort of a change to become more stable. So when you have systems that are rich in energy, for example, you have these complex molecules, these are typically not very stable, and so they will tend to move towards stability, from instability to stability. So you will have complex molecules which will have a tendency to break down into simpler molecules and to form more stable, more simple products. And because the end result is that you have, you started with a reactant that was quite complex, that was not stable, and the end product is more stable. Therefore, free energy is released as a result of this type of reaction. And as a result, this is called an exergonic reaction. Again, exer, just like exo means putting out, outward, and the gonic part, ergonic part means the energy. So energy going outward type of reaction. And in this type of reaction, the symbol for delta G is negative. And a good example of this is cellular respiration. Cellular respiration, that process that breaks down glucose, a very complex molecule, not always very stable. It goes down, it breaks that down to produce more stable products. And so for each mole of glucose that is broken down through the process of cellular respiration, you have a certain amount of energy that is now made available for work. And because energy has to be conserved, the product of the reaction then therefore are storing that amount of energy less than what the reactants started out with. And the amount of energy we're talking about is 2,870 kilojoules of energy that was stored in the bonds of the glucose molecule. And when you have the products, they contain this much less energy than the reactants, because this is the amount of energy that was released as a result. Sorry, this is not the amount of energy that's stored in the glucose molecule. This is the amount of energy that is released in that combustion reaction that we talked about. So when these molecules get broken down and reformed into these molecules. So these complex organic molecules, such as glucose being a good example of one, have to first be broken down. And when they get broken down, free energy has to be absorbed from the surroundings in order for them to break down, because they need an input of energy to destabilize those covalent bonds to the point where they break apart. And so in this part, this type of reaction is delta G is positive and is referred to as an endergonic reaction. And in this case, the process of photosynthesis to create that mole of glucose is one that 2,870 kilojoules of light energy has to be absorbed from the sun by the plant in order to produce 1 mole of glucose. And photosynthesis is a good example of this one. And cellular respiration is a good example of that. In both of these cases, exergonic or endergonic photosynthesis or cellular respiration, no matter whatever type of reaction that's taking place, some level of energy has to be added to the reaction in order to break apart the reactants. And the amount of energy that is needed to strain and break those reactant bonds, that is what we call the activation energy. Excuse me. And the activation energy, when you have provided that activation energy, then the reactants will reach that transition state where the bonds within the reactants are breaking and the bonds within the products are forming. And if we go back to our energy diagram, we can look at this. That's where that transition state is, where the reactants and products, it's in between. The reactant bonds are breaking, the product bonds are forming. This is called the transition state. And the activation energy is the difference here between the energy, the chemical potential energy of the transition state and the chemical potential energy of your reactants. This is the activation energy that was put in order to reach this transition state. Same here, this would be the activation energy that is put in to reach the transition state. So those two processes of photosynthesis and cellular respiration are complementary processes and are used as a way of capturing, storing, and releasing free energy in order to power the cell, in order to provide the amount of energy that is required to meet all the cellular processes that take place. And ATP is that central primary molecule that provides that free energy to the cell. And as free energy gets provided to the cell, this free energy is used to do different kinds of work. And there's three main categories. One of them is mechanical work. For example, you can use that energy to contract your muscles. You can use that energy for the flow of your cytoplasm within the cell, or to direct the movement of chromosomes during cell reproduction. Those are all mechanical work. And the free energy that is provided in the form of the ATP molecule can be used up for those types of processes. There's also transport work, such as pumping of substances across the membrane against the concentration gradient. Remember, when we said that when you have something moving down the concentration gradient, going from one side of the membrane to the other side of the membrane, when it's going from a position where there's lots of it on one side and going to the other side where there's not so much of it, so moving down the concentration gradient, that is a process that happens quite spontaneously, doesn't require any input of energy. But now if you want to move something across the membrane against the concentration gradient, so you want to take it from the side that there's not much of and keep on adding it to the side where you already have a lot, say you want to store this molecule and you want to pack it into a storage vesicle, then that pumping requires an input of energy in the form of ATP. Yet another type would be chemical work, such as when you're making, synthesizing, creating, building these complex molecules from simpler molecules, from simpler atoms. And ATP is that immediate source of energy. It is the molecule that powers all of these cellular processes that we talked about. ATP, or adenosine triphosphate. ATP stands for adenosine. A, T is for tri, and then the P is for the phosphate, adenosine triphosphate. That molecule looks something like this. It looks something like this. Looks something like this, actually, if you want to look at it more closely, if you want to look at its atomic makeup. And if you look at it closely, it is composed of a nitrogenous base that is bound to, and this nitrogenous base is adenine. This is a molecule of adenine, and it's a nitrogenous base. Look at all the nitrogens it has in there. This is adenine. And it is bound to a 5-carbon sugar right here, the ribose sugar. And it has 5 carbons if we count the corners, 1, 2, 3, 4, 5. It's a 5-carbon ring. It's a 5-carbon sugar called ribose. And this in turn is bound to 3 phosphate groups. Each one of these is a phosphate group. So 1, 2, and 3, triphosphate, adenosine triphosphate. And this phosphate tail is quite unstable, and the bonds between these phosphate groups, especially the last 2 phosphate groups, can be broken. And when that bond is broken, the molecule of inorganic phosphate that is released, that is removed from the ATP, then becomes ADP. and or adenosine diphosphate, ADP. Right? ATP, adenosine triphosphate, ADP, adenosine diphosphate. And here is one such reaction. You have your ATP molecule, triphosphate, 3 phosphates happening here, and then through a hydrolysis reaction that is mediated by an enzyme called ATPase. And again, remember, anytime you have an ACE at the end, that molecule is an enzyme, and typically the beginning part tells you what is that enzyme doing. This is an ATPase, so it is breaking down ATP, hydrolyzing ATP. So through the input of a water molecule, we separate one of these phosphate groups and release it as what we call an inorganic phosphate. And associated with the separation of that bond from that inorganic phosphate is also some free energy. And because this reaction is exergonic, meaning that free energy is released, then this free energy now is available for the cell to use. And now that this ADP is formed, the molecule can be recharged back to its high energy state, to go back to being ATP, if you have an addition of phosphate back again into your ATP. And I don't have a picture of that here, but we'll certainly look at that reaction as we are looking at cellular respiration and glycolysis. And so, yeah, this molecule of ATP and ADP continuously cycle through these two states of being triphosphate and diphosphate, releasing energy as is needed for the cell, and then being recharged again in the form of the high energy ATP molecule. Oh, I do have a picture of that. Right. I thought I did. Yeah, so you have this ATP molecule cycling between ADP, releasing the inorganic phosphate, and as such, releasing energy to be used for other types of reactions, for example, to make proteins, to conduct nerve signals, to contract muscles. And once you have this ADP, you can add the inorganic phosphate back to it and in a way recharge it, ready for another cycle of energy release. And in order to recharge it, you do need to put energy, and this energy, this input of energy has to come from other reactions that are exothermic, other reactions that are putting out energy. So you will take that energy and you will use it to create your ATP molecule again. And an example of this, as we discussed, is cellular respiration. Cellular respiration produces energy. It is exothermic, and it you can use that energy to build your ATP molecule back again. So this is a very important cycle to understand: the ATP, ADP cycle, the release of energy, the input of energy, and how this energy then becomes available and used up for various cellular processes, and how the energy from cellular respiration mainly is the input into creating and recycling that ATP. At this point, this brings us to the end of our lesson. And I can answer any questions that anybody has. Any questions? Okay, I just wanted to also make sure to show you guys, yeah, that your textbook, your Nelson textbook that I shared with you, has got a lot of the things that we talked about, is covered very nicely in there. Sometimes a lot of the diagrams that I use for your lesson notes are actually from this textbook. So a lot of what we talked about in our first unit is from this section. And then what's coming up in the form of cellular respiration. So today's lesson, Introduction to Metabolism, a lot of it is covered in that section. And certainly our previous lessons on some chemical fundamentals, the basics of chemistry, chemicals of life are from that section. The sequence of a polypeptide, you guys can read up more if you need to. This is an excellent resource, is what I'm trying to say. Enzymes are covered in section 1.3, in chapter 1.3. And then what's coming up is these two chapters, cellular respiration and photosynthesis, which we'll be covering in our next two lessons. I will be covering photosynthesis first. So lesson number 6, if we go down to it, is on photosynthesis. So you can go ahead and start reviewing some of the material if you like for next lesson and be familiar with it. And there's quite a lot to cover there. And then after photosynthesis, lesson number 7 is cellular respiration. And again, that is covered in chapter 3 for photosynthesis, chapter 2 for cellular respiration. And so we're going to be covering cellular respiration by next week. And our last lesson for this unit, unit number 2, is cellular energy. So we'll be talking a little bit about some of the topics there having to do with cellular energy. So you guys can read up on that too. All right, so yeah, if you don't have any questions, if anybody wants to take this time to try to go over some of the questions from some of the homework questions associated with this thermodynamic lesson, and if you have any questions, I'm here and I can answer them for you. All right, then I'm just going to take quickly a little bit of an attendance here and see. Okay, Ahmed is here, Mana's here, Natalie, Nagar, Nikki, Patrick, and Taha. Everybody's here today. Great. Okay. So, yeah, I've got all of your unit assignments. I'll start marking them, and I think I shall be able to get them back to you before our next class, before Wednesday's class. And the 2 new students who have joined in, please get your unit assignments done as soon as you can. I understand that you've only just joined, so you need some extra time, but yeah, work on those unit assignments and get them to me as quick as you can. As you've probably guessed, this is a pretty fast-paced course. Things move very quickly, and before you know it, the next assignment will be due. The next assignment is due, by the way, on October 9th will be the unit the Unit 2 assignment. That's when it will be due. All right, if nobody has any questions, I'm okay to conclude our lesson here. Okay. Nagar, you joined the class after I'd already went through some of the information with Taha, who's also another new student here. But if you want to stay at the end, and I will go through everything with you and make sure you know how to access all the different resources. And okay. All right, everybody else, I can say good night to you.
Bye, Miss.
Okay, good night, Natalie.
Thank you. Bye.
Good night,
Bye,
Ahmed.
Miss.
Bye.
Good
Good
night.
night, Miss. Bye.
Thank you.
Thank you. Good night. See you Wednesday.
Bye. See you.
Hey, Nagar.
Hi.
Hi, welcome to class.
Thank you.
What did I talk about? Oh yeah. So have you been able to access some of the material that I've shared with you in your Google Drive? Are you able to?
Yeah, I just got it today. I just checked it today.
Okay. So I just want to show you that. Let me just drag everything over to this screen and just not.
نمیشه زیادش کنی؟ نه پایینه. لطفاً. 450.
Right. So I just want to show that these are some of the things that I have shared with you. I've shared with you the biology 12.
Okay.
I've shared with you this document called recordings.
Yes, but I couldn't open it.
Okay, so if you click on it, and did you enter
Okay.
the password, the passcode here?
Yeah, but I didn't. It didn't go through. But I try again.
Oh, okay. I'll try again myself. Let's see what happens. Passcode. So we can just copy and paste that. Oops.
Oh, 174.
It should be there. Let's see. Yeah, there it is. Okay.
Okay.
So right. So yeah, give these a try. So all of these lessons are recorded. Actually, let me just stop recording. I don't need to record our conversation anymore.
Thank you.